All right, today we're jumping into a really cool corner of AI. I'm talking about the tech that powers everything from those crazy game playing bots to super efficient robots on a factory floor. We're going to break down reinforcement learning. So here's the big question, right? How does a machine learn when there's no teacher? I mean, really think about that. A lot of AI gets handed a perfect answer key to study from. But with reinforcement learning, nope, the AI is on its own. It has to figure out how to win the game without anyone telling it the rules beforehand. And the answer, well, it's actually something you're super familiar with. It learns by just doing stuff. You know, trial and error. It tries something, sees if it worked, and then tries something else. It's exactly how a baby learns to walk or how you figured out your favorite video game. Just pure interaction with the world. Okay, so let's get just a little bit technical for a second, but I promise it's simple. So in RL, you've got two main players. There's the agent, that's our little AI learner, and then there's the environment, that's the world or the game it's living in. The agent takes an action, and its one and only goal is to get the biggest pile of rewards it can over time. The dog training analogy is perfect here. The dog is the agent, it does a trick, that's the action. You give it a treat, that's the reward. It learns which actions get it the most treats. Simple as that. You know, to really understand what makes RL special, it helps to see how it compares to its siblings in the machine learning family. First, you have supervised learning. That's the book smart one, right? It's like having a teacher who gives you all the problems and all the answers. You just memorize them. Then there's unsupervised learning. That's the detective, trying to find clues and patterns in a huge pile of data with no instructions. But reinforcement learning, that's the daredevil, the adventurer. It just jumps into the world and learns by being rewarded for good moves and penalized for bad ones. So how does this whole trial and error thing actually work? What's the engine driving it? Well, it all comes down to a really simple but powerful feedback loop. Okay, so look at this. This loop is the absolute core of RL. It's a constant back and forth. Our agent, our learner, takes an action. The environment then responds with just two pieces of information: what the new situation looks like, that's the new state, and whether that action was good or bad, which is the reward. That's it. This simple little dance, repeated over and over, is literally how it learns everything. So let's walk through that loop one more time, step by step. Step 1, the agent looks around and figures out, where am I right now? That's the state. Step 2, based on where it is, it decides, okay, I'm going to do this. That's the action. Step 3, the environment gives it feedback, a reward or a penalty. And finally, step 4, the agent is now in a new spot, a new state. And then the whole thing just repeats, again and again, sometimes millions of times, until it slowly builds this map in its head of what to do to get the most rewards. But this whole system creates a massive dilemma. It's a problem at the very heart of reinforcement learning. So imagine the agent has found a strategy that works pretty well. It's getting decent rewards. What should it do now? And this brings us to the classic trade-off, explore versus exploit. Think about it like choosing a restaurant. Exploitation is when you go to your favorite spot. You know the food is good, it's a safe bet, a guaranteed decent reward. Exploration is trying that new place that just opened up. It could be terrible, or it could become your new favorite. So does the agent stick with what it knows works, or does it take a risk to see if there's an even bigger payout out there? And this graph right here shows you exactly why this is so important. Look at the gray line. That's a greedy agent. It only exploits. It finds a pretty good strategy right away and just sticks with it. See how it flatlines? It gets stuck. Now look at the blue line. This agent mostly exploits, but every once in a while it takes a random action. It explores. It might seem a little slower at the very beginning, but look what happens over time. It blows the other one out of the water because that little bit of exploration helped it find a way better strategy in the long run. It's absolutely critical. Okay, this is all cool theory, but let's get real. Is anyone actually using this stuff in the real world, or is it just stuck in research labs? The answer is yes, absolutely. But it's not always easy. So here's a quote from someone working in e-commerce. They say they use these exact principles to optimize everything on their websites, the layouts, the design, what messages you see. They're constantly running little experiments to see what gets people to click more or buy more. That is a perfect real-world example of that explore-exploit idea in action. But on the flip side, here's a reality check. Another person from the industry says that getting RL to work is, and I quote, insanely hard. Why? Because the real world isn't a neat and tidy video game. It's messy, it's complex. When you try to apply RL out there, you run into all the hard problems of the real world all at once. But even with those challenges, the impact is undeniable. I mean, think about it. Recommendation systems on sites you use every day. That's often RL. Robots learning to assemble things in a factory. RL. Making our energy grids more efficient. Yup, RL. And of course, the most famous examples, AIs that can beat the best human players in the world at super complex games like chess and Go, that's all powered by these ideas. So we've seen how AI can learn a task. But what's next? What's the next big mountain for AI to climb? Well, it turns out to be something that you and I do without even thinking about it. Remembering. I mean, really think about this for a second. You can spend weeks, even months, training an AI to be a grandmaster at one specific task. But what happens the moment you say, okay, great job, now I want you to learn something completely new? What happens to all that knowledge it just worked so hard to get? Well, what happens is a huge problem with a very dramatic name, catastrophic forgetting. It's pretty much what it sounds like. When you teach a standard AI something new, it basically overwrites its own brain. The connections that stored the old skill get rewired for the new one, so it literally forgets everything it knew before. And you can see why this is a massive roadblock if we want to build AIs that are truly smart and can adapt over time. So where do we find a solution to a problem like this? Well, like so many times in AI, researchers are looking at the one system that has already figured it out, our own brains. Your brain has this amazing two-part system to avoid this exact problem. You have the hippocampus, think of it like a temporary notepad where you jot down new stuff really quickly, and then you have the neocortex, which is like your long-term hard drive. Overnight, your brain slowly moves the important notes from the notepad to the hard drive, integrating them without wiping out what's already there. It's genius. And that beautiful biological system is the direct inspiration for the next big thing in AI research. It's a field called continual learning. And the goal, really the holy grail, is to create an AI that can learn sequentially for its entire existence, one that can pick up new skills while holding on to the old ones, building a lifetime of knowledge, just like a person does. This is where the most exciting research is happening right now. So when you step back and look at it, the whole field of reinforcement learning is on this incredible journey. It started with simple ideas, like a little robot figuring its way out of a maze, and now it's tackling these massive, ambitious goals, trying to create an AI that can learn and grow forever. And that really just leaves us with one final, huge question to think about. If we actually crack this code, if we can solve catastrophic forgetting and build an AI that truly learns throughout its entire life, what does that future look like? What could be possible then?